Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with the time series modeling and that too the aspects of volatility modeling. So, let us see how is this kind of structure. Okay. So, this were the kind of discussions technically. Before I start, so basically the time series modeling can be of two types, whatever we have discussed earlier, and one is called as the linearity structure and the other one is nonlinearity structure. In the linearity structure we have discussed in fact three different forms. One is called as autoregressive scheme, then moving average scheme, then autoregressive moving average scheme. So, that is the kind of item which we have discussed earlier, and basically autoregressive schemes, it is the structure of lag concept, and we have two different types of lag modeling. One is the autoregressive, the other one is the distributive lag modeling. So, which we have already discussed, and then the kind of moving average. We start with the simple estimation process and then have the error term, then finally, the dependent variable can be connected with the lag of the error terms. So, technically, so if you go through this ARIMA structure completely, so it's basically depends upon y t as a function of u t minus I and y t minus I. Okay. So, this is how the kind of structures. So, one instance we are just connecting y t with lag of y t, that is what the autoregressive scheme, and sometimes if there are more number of variables, the y t can be connected with the another variables and that to lag variables. For instance, we can have like this y t as a function of y t minus I, and in other case we may have like this y t as a function of x t minus j. So, that means, if y t is a kind of time series variables, it may be connected to any engineering problem, but the requirement is that we must have a time series data, and that too the time series must be consistent, whether it is a day wise information or monthly information or weekly information or annual information. So, it must have consistency with the time, a particular time that is with reference to hour, day, week, month and the kind of an annual, even if quarterly data, and then we from that data structures we can create a lag variables. So, now having actually a particular variable say y t, so we can create a number of lag variables, provided sample size should be very high, and in the same times there should be they should maintain some kind of consistency. So, means technically there should not be any gap in between, or there should not be any kind of inconsistency in the process. The other form of model is we have a two different variables like y t and x t, but the dependent variable y t can be function of lag of another variable say x t minus j. So, that means, x t j variables, and by default the lag will be x t minus 1, x t minus 2 and so on. And if the model is with respect to the first ones, where y t as a function of lag of y t, then that is what the structure called as a autoregressive structure, and we call as autoregressive model, and which we have already discussed. And the second one is y t while function of x t minus j, that is called as a distributive lag models, DLM. Now, we can have a structures like this y t equal to function of y t minus I and x t minus j. Okay. If this is the kind of model which we call as ARDL model. Okay. So, that means technically it is called as a autoregressive distributive lag model, and means this is one kind of cluster in the time series setup, simple autoregressive model which we have already highlighted, and then a distributive lag model which in fact also highlighted, and then by if you combine the ARM scheme and DLM scheme, then we have a structure called as ARDL scheme, that is called as a autoregressive distributive lag model. The structure of this ARDL is y t as a function of y t minus I and then another variable x t minus j. Not necessarily it will be bounded with only two variables, it can be extend to multiple variables, but every times there is a dependent variable and we connect with the lag of this dependent variables and lag of some other independent variables. That is what the RDL structure is all about. The other form is the autoregressive, then moving average, and then finally ARMA, like ARM, DLM and ARDL. So, we have here AR, then MA, then AR MA. So, that means technically autoregressive, then moving average, and then finally autoregressive moving average. So, technically here the dependent variables y t as a function of y t minus I, like the case of RDL, where we are connecting y t with lag of y t, that is the autoregressive part, as I means like the case of ARM and the kind of ARDL, and another form is y t as a function of u t minus I. So, that means technically we first connect with the y t with the one of the lag terms or any other variables, then trying to find out the error terms, then finally y t will be connected with the lag of these error terms, and then we will connect a scheme where dependent variable as a function of these lag of these error terms. So, if that is the case, that is called as moving average schemes, which we have again discussed in the last lecture. So, whether it is a scheme of ARM, DLM or ARDL or the scheme of AR, MA or ARMA. So, it exclusively depends upon time series setup, and variables must be clear and problem must be correctly identified, and the fit of this kind of models or the use of this kind of model typically requires the time series data, whether it is a kind of simple management problem or any kind of engineering problems, but usually in the management having the financial data. So, we have lots of time series structure, but similarly in most of the engineerings we have a time series data, and then these models can be very easily fitted there, which we have already discussed some extent, and there is no issue about connecting to any engineering problems while time series data is there in the system, and in any forms once it is clear, then you can use these models subject to availability of time series data. The other form of time series modeling which you are interested to discuss in this lecture is the nonlinearity part, and that too again the time series structure. So, whatever we have discussed this side. So, the starting with the ARM, DLM, ARDL and AR, MA and ARMA. So, that is the structure called as linear time series structure, and the counterpart will be by default called as a nonlinear time series setup. Here we have also different kind of models, but typically we will highlight three types. One is the structure called as arch and GARCH cluster, arch clusters, then GARCH clusters, and then artificial neural network clusters, okay, artificial neural network cluster. And arch clusters, again arch and GARCH depends upon error term typically. So, like the kind of moving average. So, we start with a simple model first, that means technically both for arch and GARCH, that is one cluster, then artificial neural network is the another cluster, but both these techniques are in the basket of nonlinear time series modeling. So, in this case we start with let us say 2 variables, but not necessarily every time 2 variables, it can be extended to multivariable case. So, here if you start with y and x the 2 variables. So, first you connect with y t as a function of x t or vice versa x t as a function of y t, and after estimations you may have the component called as u t, that is what called as error terms. And we have discussed lots and lots problem to connect how dependent variable and the independent variable connected, and how to get the estimated output, and then how to derive the predicted dependent variables, that to let us say y t is a dependent variable, then we need to have a y estimate, that is what the predicted variable, and then with the help of dependent variable y t and the estimated dependent variable y t cap, we will find the error terms, right. So, after getting the error term, so we can have actually the structure called as log of the error term, starting with u t, then u t minus 1s, and then u t minus 2, and so on like that. That is one kind of cluster. Again we can have a nonlinear structure like u square t minus 1, u square t minus 2, and so on. So, in the previous case we are using the linearity structure. Now, we will connect within nonlinearity structure, where instead of u t minus 1, u t minus 2, we like to connect with u square t minus 1, u square t minus 2, and so on. The beauty of this particular structure is that if you connect with u t with u t minus 1 etcetera, then there is a high chance that the mean of the error term will be close to 0, but when we go for squaring these error terms, then by default we have a significant impact, and that impact can actually considerably having effect on the dependent variable. So, compared to linear structure, the nonlinear structure has actually more kind of informative, because we are we are transferring this information in a kind of setup where it can produce some kind of a significant impact to the system. So, technically using simple the log variables, we like to use the square of these log variables, that means technically u square t minus 1, u square t minus 2, and so on. Simply the first means the step is like this: you can have first error terms, then create log of these error terms. For instance, if u t is the error term, then the log of these error terms will be u t minus 1, u t minus 2, u t minus 3, and so on. And finally, you can create a u square t minus 1, u square t minus 2. That means, we are just bringing into a some kind of structure. So, that means, the advantage is that if you square, then so the value will be coming differently. So, as a result, so it can produce some kind of significant impact to the system. And again, it is not the question of u t with the square of the error terms. That is what the cluster called as arch cluster, and technically it is called as a autoregressive conditional heteroscedasticity. Means just it is a counterpart of homoscedasticity, where we have a uniform error variance, but here in this case we have a heterogeneous error variance. That is what the term called as a heteroscedasticity. So, that means technically before you start analyzing the cluster called as arch and GARCH clusters. So, simple understanding is about heteroscedasticity, and that is the first and requirement, and your understanding must be clear there. and then we will come to the ARCH cluster and the GARCH cluster. We have a series of models on this particular cluster. Typically, we start with error terms, then trying to explore the heteroscedasticity issue. Of course, we have already discussed heteroscedasticity issue, which is actually typical virus before start doing the doing the kind of estimation and the kind of predictions, etc. So, that means technically once you get estimated model and the error terms. So, that error terms behavior should be should be analyzed properly, and starting with heteroscedasticity and homoscedasticity. Homoscedasticity is good for the modeling, but heteroscedasticity is not is just negative impact to the modeling. So, we try to minimize the heteroscedasticity issue, but the structure of the time series data is that heteroscedasticity means when we have some kind of heteroscedasticity problem to the system, then we will have the kind of different system where we can use this kind of model, that to nonlinear time series model, and that to ARCH cluster and GARCH clusters. So, so first of all the kind of understanding of the heteroscedasticity, then the autoregressive scheme, and then the some of the condition we have to cite, and as a result we can have the model called as autoregressive conditional heteroscedasticity. So, autoregressive is one part, heteroscedasticity is another part, and the kind of condition which you are setting there is called as ARCH clusters, like which we have already discussed in the case of ARMA cluster, where we are taking care of autoregressive scheme and moving average schemes, but ultimately in between there is a technical term called as order of integration. So, that is why instead of saying ARMA, so we call as ARIMA. So, like this this is what the kind of structure called as ARIMA. So, autoregressive integrated moving average, what is that typical name. So, that means before we start the ARMA process, so we are supposed to check the stationarity of the variables, and that means technically we need to check the order of integration through which the variable the typical variable will reach the stationarity, and until unless the stationarity and the kind of an order of integration, then this kind of model will not give you solid kind of structuring or the kind of restructuring to predict certain things. So, that is why a unit root is very much required to justify the situation and the kind of requirement. The similar kind of flow is with actually ARCH and GARCH cluster and the artificial neural network cluster. So, here in the ARCH clusters, so we are just connecting UT with the error of these means square of these error terms, that too in the with the help of log structure, and the typical cluster is called as ARCH cluster, and its extension called as a generalized autoregressive conditional heteroscedasticity, where we like to connect error term with square of the error variance, that is what called as a sigma square UT. So, that means technically, so we can have u square t minus 1, you can have u square t minus 2, this is one kind of cluster. The another kind of cluster is you can call as sigma square ut minus 1, sigma square ut minus 2, so like this is another cluster. So, that means this is what called as error variance, as we have already discussed this one. Sigma square is the error variance, which is actually some of the errors, some of the squares of the errors with respect to the degree of freedom. So, that means when we have a time series data, so we can easily get the log components and the square of these log components, and then finally the log of these error variance. So, now every time in this ARCH and GARCH clusters, the typical error term need to be predicted with its log variables, and that through square of these log variables and the square of the error variance. Okay. So, means error variance with respect to the log part. So, technically the first cluster will be ut as a function of u square t minus I. That means, technically the way we have written here y equal to function of y t minus y e and y t equal to a function of x t minus t minus j. So, here one particular cluster will be like this u t as a function of u square t minus I. So, this is one particular cluster, and then another cluster will be u t as a function of u square t minus I and then sigma square t minus j. Okay. So, sigma square, of course, sigma square u t minus j. So, that is what the basic structure of arch versus a GARCH. So, the autoregressive conditional heteroscedasticity and generalized autoregressive conditional heteroscedasticity. So, typically we put lots of condition. Of course, GARCH has lots of extension, and in fact, arch also having a similar kind of extension. For instance, you can have a arch cluster of 1 to 1 and the kind of 1 to 2 like this, and then GARCH clusters against like ARMA clusters. So, we can have the GARCH clusters. So, 1 1 2 2 3 3 like this. So, then we can design the models. Mathematically, it is well established. You can just start with the game with 1 1 structure, 2 2 structure. It looks very decent to do the modeling, econometric modeling, and the that too for engineering econometrics. But ultimately, the use of this model and the kind of experiment, the kind of used to predict and the kind of forecasting. So, problem should be exactly on that particular framework, and most important is the data part, and which must have in a time series setup. Then you can go ahead with this kind of models and do the kind of prediction and forecasting as per the particular engineering requirement and the need of the decision making process. And then we will discuss in details in about the arch cluster and GARCH cluster, because the ARMA part we have already covered in the last lecture. Since we are discussing nonlinear time series, just I am connecting how there is a kind of extension which you can have here in the form of arch cluster and GARCH cluster, and then finally we connect with a concept called as a neural network. Okay. Because we are connecting again with a linear to nonlinear setups, and by default artificial neural network will be in that particular similar kind of cluster. So, here the log component is not a big deal, but what is the big deal is the variables will be connected with a different functional form, that too in a nonlinear structure. And typically for artificial neural network, the same two variables can be connected instead of simple linear equation. For instance, y versus x, we can put y equal to simply alpha plus beta x. That is what the linearity structure. If not, neural network structure will follow the sigmoid functions, which is actually nonlinear in character, like exponential functions or logarithmic function, and then do the processing, and then do the estimation to predict the dependent variable with respect to the independent variables. So, overall structure is that. So, we have the system called as as in nonlinear time series modeling, and that too will cover three things: the arch cluster, GARCH cluster, and artificial neural network. Of course, more important is the arch cluster and GARCH clusters, which is very much important, and that too to maintain the continue with the autoregressive, distributive log, ARDL, autoregressive again moving average, and then ARMA. Then similar cluster we are just extending to arch and GARCH clusters, and in between you will find there are many such GARCH models like eGARCH, GGARCH, and so on. So many things are there, and again every times the extension of arch and GARCH, and that in between this arch clusters you will find plenty of different type of models, and that too again with respect to different conditions. So, we put different condition, and then the model extension will start, and that will be having more flexibility, and add to the modeling basket how you can predict any kind of engineering problems. subject to the time series data, and then the kind of the use of the nonlinear time series models. Now, with this actually we are just highlighting how is this kind of volatility modeling, and technically I will just highlight the issue of nonlinearity first, and then I will come back to the arch and GARCH cluster, and again slightly I will touch upon the artificial neural network. Then here the motivation is actually we have gone through the linear structural framework, and that too in time series model. That we some of the important functions or features we cannot actually typically analyze while handling financial data and engineering data. For examples, the Cortesis and volatility clustering and volatility pooling, and there is also leverage effects. And coming to traditional form of models, that in a multivariate framework start with a dependent variable y equal to simply beta 1, beta 2, x 2, beta 3, x 3 and so on, and where we are assuming that error term will behave with mean error, mean of the 0, and then error variance sigma square. Now, the issue of nonlinearity will come, that too for a arch cluster and the GARCH cluster, where the error term will not actually follow sigma square u, that is what the homoscedasticity. It will be forming a structure called as a sigma square u I. That means technically instead of saying u t, which is actually let us say normally distributed with 0 and unit variance, that means this is actually mean of the error term, and then this will be called as variance of the error terms. Okay. So, that is what called as a sigma square u, and so when we have a sigma square u like this, that is what the game of called as a homoscedasticity, which we have actually discussed earlier. But if not, then the structure will form a kind of problem like this sigma square u I. So, that means error variance will not same over the time. So, it will be having different values with respect to different time frame, and if that is the case, what is called as a heteroscedasticity problem. So, now we are doing the extension of the heteroscedasticity problem, and that too in the form of arch cluster and GARCH clusters. So, what we can do? So, how is the arch cluster and how is the GARCH cluster, and that is under the basket of nonlinear time series modeling. So, we can start with a simple problem and then connect with the time series data, and once you do the estimation and then get the error term, and this kind of model by default will be coming into the picture, and they do the kind of predictions and the kind of forecasting as per the engineering requirement and the kind of means as per the decision making process. So, we have beautiful structure through which you can generalize this issue, and typically the structure is yes. So, this is what the error variance, and if you look into this particular nonlinearity structure and that to arch and GARCH cluster, this is how the kind of structure where we can exactly apply the nonlinear model, and that to arch cluster, GARCH cluster and artificial neural network. So, that means we like to just plot these variables with respect to different time periods and check whether there is a kind of volatility signal or not. So, volatility means very simple language, there are lots of ups and lots of downs, and as a result the situation is not so stable. So, that if the situation is not so stable, that is what we call as volatility. So, within the volatility structure instability case, how we can bring better and better and better prediction to the particular engineering problem and as per the requirement. So, arch and GARCH cluster can give better such kind of clue to deal with these problems and do the kind of better forecastings and the kind of engineering requirement. In the next class, we will start from here and then we will connect with a problem with this particular models, that to Arch cluster and GARCH cluster. With this we will stop here. Thank you very much.